So in terms of acid-base chemistry, acid-base chemistry is at least in this discussion is nothing more than an equilibrium. That's why it's so critical to understand equilibrium, because
I thought it'd be a
equilibrium
big old X.
equilibrium will allow you to, yeah, just watch out for your audio. You might want to mute that when you enter the room, otherwise the whole class will hear. Okay, back when I just
Well,
Man, that fucking axe is gonna be so nice for questing. That's like
yeah.
13 DPS
okay,
upgrade, not even mentioning the stats on it.
Right.
Is it better than the Raptor?
mute. Okay, um, let's see. Okay, in terms of this acid-base chemistry material, um, go ahead and do this. So what we have here is an equilibrium process, and the equilibrium involves proton transfer. What happens to an acid is that it donates its hydrogen, and sometimes it could release it. So the definition of an acid base is based on Bronsted-Lowry, and acids are defined as acid are proton donors. Protons, you recall, are nothing more than hydrogens stripped with its electrons. Bases, on the other hand, are referred to as proton acceptors. That is, they accept the proton. Um, Here are some examples. Oops, sorry. The examples here is hydrochloric acid dissociating to hydrogen ions and chloride ions, or ammonia going to NH4 plus, that's a base. Now, of course, in the reaction between these two, the hydrochloric acid donates the proton, and the proton here, okay, let's see if I got a pointer. The proton is going to be transferred to the ammonia, because ammonia has a lone pair, and you get ammonium. Remember, ammonia is NH3, ammonium is NH4 plus. There's a difference. And then the hydrochloric acid now becomes the chloride. Later on, you guys will see that these are conjugate pairs, and we'll be defining that shortly, because conjugate pairs are sort of an important concept. In an acid-base chemical reaction, hydrogen and hydroxides always combine to form water if you have the hydrogen ions and the hydroxide ions present. But as you saw from this example right here, it's not necessary to form water in the case of an acid-base reaction. All you've got to do is transfer the hydrogen to one of the chemicals. So go ahead, and so here is that reaction again. And you see how NH3 ammonia converts to NH4 plus? Well, that just tells you that these two are conjugate pairs, okay? These two are conjugate pairs. And conjugate pairs always differ by one hydrogen. These two are conjugate pairs as well. And notice how they differ by one hydrogen. When a conjugate pair, when an acid-base reaction occurs, what happens is that the hydrogen is transferred. And now if you look at the products, the base becomes the acid, the conjugate acid, and the acid becomes the conjugate base. So that's something about acid-base chemistry, is that you do get these conjugate pairs that form. And so we say that NH3 is the conjugate, is the Bronsted-Lowry proton acceptor, and it's the conjugate base because it's the proton acceptor. Chloride ions, which is the other side of the reaction, is the Bronsted-Lowry conjugate base as well, because it's the proton acceptor if you look at the reverse direction, okay? So whenever you have conjugate pairs, one will always be an acid, the other will always be a base, okay? So keep that in mind. Let me just clear this up real quick. Here are other examples of conjugate pairs. You can see that this is called bicarbonate right here. It's called bicarbonate. And the bicarbonate becomes carbonate ions after it transfers its hydrogen. So you can see right here that this chemical right here becomes that. And so these two would be conjugate pairs because again, they differ by hydrogen. Water now is going to be a base in this particular case because it accepts the hydrogen and it forms hydronium. So to identify this, this would be the conjugate acid, this would be the conjugate base, but in the reverse reaction, this would be the conjugate acid and this would be the conjugate base. Remember that acids are defined as the chemical that donates its hydrogen. The base is defined as the chemical that accepts the hydrogen. So that basically is how we do that. And the other example, of course, is it doesn't have to be water. It could be hydrogen sulfide or some other chemical that is willing to accept that hydrogen. Okay, so here's another example of conjugate pairs. And just move on here. So you can see this in terms of the definition. And of course, these are more examples. And so again, you can just recognize conjugate pairs because they always differ by one hydrogen. So if the question is, give the conjugate pairs of NH3IO minus, C2H3O2 minus, and HASO4, you can actually do this by, doing this. If I had NH3, you can actually make this NH4 plus, and you notice that it's picked up a hydrogen in the process, or it can donate a hydrogen and become NH2 minus. So what happens is that these two are conjugate pairs, or these two are conjugate pairs because they differ by hydrogen. These guys, however, are not related. These are not conjugate pairs of each other because notice that they differ by two hydrogens. So just to let you know, again, about recognizing conjugate pairs. And later on, you'll see that conjugate pairs are important because then if an acid becomes a base and the acid is a fairly strong weak acid, the base becomes a fairly strong base. It becomes the opposite. So again, here are more examples of conjugate pairs. And at this point, you guys should be able to recognize them. Okay. So if you take a look at this list, and this is in your book, here are the acids, here it's conjugate pairs. Remember that acids are defined by their ability to donate its hydrogen. So the more willing it is to donate the hydrogen, the stronger that acid. These chemicals at the very top, well, those chemicals at the very top are the chemicals that are going to donate their hydrogens willingly. That's why they're called strong acids. These right here are weak acids because they don't give up their hydrogens that readily. Their ionization to a hydrogen and its counter ion is less than 100% of the time. And these are very, very weak acids. In fact, they're negligible. They're not considered acid because they don't want to donate their hydrogens. But look at their conjugate pairs. If you look at their conjugate pairs, the acids, the very strong acid becomes a very negligible base. The conjugate is totally the opposite. Not only does the strong become the weak, but the acid becomes the base. Here, you can see that if this is a fairly strong weak acid, this is a very weak base. Here, where we had negligible acids, they become very strong base in their extreme. So the conjugates always becomes their anti-self. Okay, so that's important because if you only have information about one of the chemical, then you can infer about its conjugate based on the fact that it's opposite. So here's the more extensive list. These are the names of the acid. You guys should at least get yourself a good list of the names of the acids and their formula, because that if you're going to be taking an MCAT, you should know what these acids and their conjugate base happens to be and their name. You won't need to know their Kas or their pKas, but you should know something about their formulas and the chemistry that dictates their behavior. Okay, so and the way we recognize whether these things are strong acids or strong base is by recognize their ability to give off their hydrogen, and so that's dictated by the equilibrium constant. So here you can see that strong acids undergo dissociation 100% of the time. Strong base picks up or donates hydroxide or picks up hydrogen 100% of the time. And so if we have a chemical like perchloric acid, and remember that was one of the chemicals that we listed as a strong acid, if we have 0.001 molar perchloric acid, and I ask you to tell me the concentration of the hydronium, well, because it's 100% of the time, the hydronium will also be 0.001 molar, because this thing converts to product 100% of the time. So remember how to take the pH of a chemical based on the hydronium ion concentration. We talked about that last time. It's basically the negative log of the hydronium ion concentration. And if you do that math, it becomes 3. So the pH of this solution of a 0.0010 molar solution of perchloric acid is a pH of 3. Okay. So here's the base. And this is a tricky base because even though this is a strong base, look at the chemistry. Always pay attention to the chemistry when you do acid-base chemistry. That way you won't be tricked. Here you have calcium hydroxide. And you know that calcium hydroxide is a strong base. Why? Because according to the solubility rule, alkali salts, alkali are group 1. It has group 1 or heavy group 2. And calcium is a heavy group 2. Calcium is an element that has a higher molar mass than magnesium or atomic mass than magnesium, so it's heavy group 2. These readily dissolve, and if it readily dissolves, it means that it gives up its hydroxide 100% of the time, okay? That's what defines it as a strong base, but notice it gives up 2 hydroxides. So the concentration of hydroxide is not 0.001, but 0.002, because it does this at 100%, but 2 hydroxide comes off for every 1 calcium hydroxide. So please always pay attention to the chemistry. That way you're not fooled in terms of a simple question like, if I gave you a 0.001 molar concentration of calcium hydroxide, what is the pOH? And the pOH is not negative log of 0.001. It's a negative log of 0.002 right here, okay? So as I said, weak acids and strong acids are one that dissociates 100% of the time as well as base. Weak acids do not. And so there's an equilibrium that is involved in this process. This process requires an equilibrium right here. And because it's an equilibrium, what we have is a equilibrium constant. And that equilibrium constant is called the Ka. And you know it's a Ka because the product is an acid. The reverse, if you had a base, then the equilibrium constant for a base undergoing reaction would be called a Kb. And you know it's a Kb because in a Kb situation, okay, in a Kb situation, what happens is that if you have a say NH3, NH4, NH3 in terms of water. And here water is the acid and ammonia is the base. So what you have is you have NH4 plus and hydroxide. So what water does is it will donate its hydrogen to ammonia. And this is a KB. And how do you know it's a KB? Because you form hydroxide. So the product that is formed in a acid-base reaction will dictate whether you have a Ka or a Kb, okay? And these are just equilibrium constant for that particular reaction. So again, here are again more an extension of this slide. Less than 100% dissociation, you have a weak acid or weak base, and both are equilibrium problems. Let me just make sure you understand. When you have, let me change my ink here, okay. When you have a strong acid or base, the problem is stoichiometric. And that's because it's 100% reaction. And when it's 100%, there are no equilibrium involved. On the other hand, when you have weak acids or bases, then the problem is equilibrium. And you have to solve the ice table in order to solve that problem. Because what happens is that you have to figure out how efficient is that proton transfer. And the efficiency of that proton transfer, or the efficiency by which the chemical accepts the proton, is based on the Ka or Kb. Okay, so please keep that in mind. So let me go ahead and okay. So here are some Kas of acids, and notice that these are the formulas, and what's highlighted here is the acidic hydrogen, the hydrogen that comes off. And notice that some of these chemicals have more than one hydrogens. That can actually, all these chemicals only have one hydrogen. That's why they only have one Ka. But among the Kas here, this is the largest. Okay, this is the largest among the list. And this is the smallest among the list. So in terms of acid-base chemistry, among weaklings here, this is the strongest weak acids, whereas this right here would be the weakest weak acid. And how do you know that? Look at their equilibrium constant. This tells you that this has a greater efficiency in terms of donating its hydrogen than this chemical down here. So again, equilibrium plays a role in acid-base chemistry. Yeah, exactly. For some of you who wrote in the chat, if you have acid-base chemistry, it's solved exactly as what we learned in the previous chapter. Okay, so there's nothing new here. Only their identity has changed. Only their identity has changed. Okay, so when you're solving weak acid problems, this is what you're going to do. It's the same as when we did equilibrium. You definitely need to balance the equation. Okay, you definitely need to balance the equation. And The reason why you need to balance the equation because you need to write the mass action expression. But the mass action expression is actually easier than in chapter 15 because it's always going to give you one hydrogen. Even if it's a chemical that can donate more than one hydrogen, you have to treat the dissociation, that is the release of hydrogen, one at a time. You got to construct an ice table. You have to use the variable x in terms of how much of the hydrogen is released and how much of the hydrogen is picked up. And then you solve for x in terms of figuring out how much of the product forms, as we did in chapter 15. And then just double check your assumption, make sure that the 5% rule applies. Here in acid-base chemistry, because you're generally dealing with chemicals with K equilibrium of 10 to the minus 3 or less, you can, the first iteration in the basic assumption method will basically work when you solve these problems. Okay, so that's good in terms of dealing with some of these problems. Even though the problems, the math might be easier for acid-base chemistry, it can get complicated. And the reason why it gets complicated is because some chemicals, which are called polyprotic acids, you have to solve several problems. But what you will see is that, oops, sorry. What I'm showing you is actually a movie of my PowerPoint slide, because if I do a PowerPoint slideshow, then I don't have access to the writing tool. So what I did was when I saved my PowerPoint, I made it a movie. And so that's why you see this, controller down here. And I'm just making it go one frame at a time. So to solve this particular equilibrium process, you got to assume that there's always going to be water. And if there's water, you can always assume that the hydronium ion in that water is about 1 times 10 to the minus 7, which we can assume to be negligible, okay? Weak acids have very small Ka, and therefore X is very small. And we can make this basic assumption here that the equilibrium concentration of the acid is essentially equal to the initial acid concentration. And you see that in the problems that we work out shortly. Here's an example of hydrofluoric acid. In hydrofluoric acid, what we have here is HF donating its hydrogen to water. And we know that HF is a weak acid. So again, what does that mean? It means that if you have 100 molecules of HF and it forms product, then what will happen is only a small percentage of that HF will dissociate. Let's say like 3 out of 100. So at equilibrium, you got 3 hydrogen ions for every 100 HF molecules and 3 F minus for every 100 molecules. Again, this is an exaggeration, but I just want to illustrate to you that that's what weak acids and base do. They don't do it stoichiometrically. They do it less than 100% of the time. And what dictates how much product is produced is the equilibrium constant for that particular reaction. So again, you can see that in this particular case, what we have is, oops, the ice table. If we have HF here at 0.1, and water, of course, is a liquid, so I just put a lot there. This particular, excuse me for that, this particular column is going to be neglected. And the reason why it's going to be neglected is because, remember, this is a liquid, so it never shows up in the mass action expression. Because it's in water, you can always assume that the hydronium is going to have an initial concentration of 1 times 10 to the minus 7. But again, we're going to ignore this because it's going to be, we're going to assume it's small, okay? So we set up our ice table. This thing will dissociate to minus X. This will be plus X plus X. And so at equilibrium, what you have is 0.1 minus X, 1 times 10 to the minus 7 plus X, and then X here. And we could ignore this because we can assume that x is bigger than 1 times 10 to the minus 7. That's one of the assumptions that you have. And so you get this mass action expression right here. And you see how simple it is? It's basically hydronium times fluoride divided by the concentration of HF. And what we're going to do is we're going to make a simplifying assumption. Why do we do that? Because this equilibrium constant is small. And so we can say that this concentration right here is approximately 0.10. And then we can verify the 5% rule. Okay, so go ahead and clear that. And so here's a detailed problem in which I have 0.10 molar of hydrofluoric acid and 0.10 molar of hydrochloric acid. Remember, hydrochloric acid is a strong acid. So you don't even have to pick up your pen to figure out what the pH is, because the hydronium concentration of hydrochloric acid is going to be 0.10 molar. And the pH of 0.10 molar, 0.10 molar is 1 times 10 to the minus 1. So that'll be a pH of 1, okay? But that's totally different from hydrofluoric acid, because if you have hydrofluoric acid, okay, what you have here is you have to work out the equilibrium problem. You have to work out the equilibrium problem. The Ka here is 6.8 times 10 to the minus 4. So when you set up the ICE table and you have X for fluoride, 1 times 10 to the minus 7 plus X for hydronium, and this right here will be your HF concentration. After making some assumptions right here, you have X squared over 0.1, and so what you have after doing the math is X squared is equal to 6.8 times 10 to the minus 4 times 0.1, and if you take the square root of that, you get a hydronium ion concentration of 8.25 times 10 to the minus 3. If we verify our assumption, and how do we verify the assumption? Let me show you that real quick. Okay, we verified the assumption based on the fact that here's the simplifying assumption method. My thing went to sleep, so yeah, wait that up real quick. So how do I know that I surpassed I need to do a second iteration? Well, here you can see that the sorry about that. Here you can see that to verify the assumption, you have to look at delta X over X or the initial concentration of your acid. So delta is how much X is, and that's 8.25 times 10 to the minus 3. And our initial concentration of our acid was 0.10. And so if you multiply that by 100 and we work out that math, that actually comes out to 8.24%. So that's bigger than 5%, so we have to do a second iteration. And how do we do our second iteration? We have to go back to our basic assumption. Our basic assumption was that the equilibrium concentration of the acid is going to be equal to the initial concentration minus X, but X is not 0 anymore. It's actually 8.25 times 10 to the minus 3. And so what we need to do is we need to make this equilibrium concentration a better value. And we can do that by doing this 0.10, which was the initial, minus 8.25 times 10 to the minus 3, because that's our first approximation of X. And now if we do that, we come up with a value of 0.0918. Now, if you round this off, it's to one significant figure, it's 0.1, but again, because we're making that initial assumption better, we're going to have to use this. And so you can see this right here in this problem, okay? In this problem, you can see that assumption right here. That's where we made that adjustment, and we put that in and we solve for x again. And this, if you do this enough times, it's much faster than a quadratic. Of course, if you do a quadratic, you always get the exact solution, but that means that you have to have a quadratic calculator or work out the math. If you do that, doing a simplifying assumption, actually, if you know what you're doing, is a lot faster. Now we have a better number. We have 7.9 times 10 to the minus 3. And we can see again the change versus the initial concentration. That's only 0.38%, and that definitely is better than the 5% rule. So that's how you would do a second iteration on the simplifying assumption method. Remember, simplifying assumption method, you're making assumptions that may or may not be valid. But if you do a second iteration, it makes that number better. So this is a typical problem that you work on in acid-base chemistry, okay? So here are more examples. And again, you can see here that they're doing simplifying assumptions. Here, the initial concentration of this particular propionic acid, you have 0.12 here. And here, the first iteration works because it's less than 5%. So it's okay in terms of this particular case. So let me move ahead. Here's a second example because I wanted to illustrate to you guys, again, more of these things. You just need to practice it. And here's where I picked up that if the initial divided by Ka is greater than 400, then generally one iteration will work. But if it's less than 500, you generally would need 2 iterations. This is the book that I used in the past that gave you some sort of a way to double check whether simplifying assumptions is going to be valid or not, whether you have to do 2 or more iterations. And this book this particular concept is not introduced in our textbook, but it was introduced in another textbook that is still out there. It's Silverberg, just so that for those of you who wants to know. Okay. So let's take a look at this concept called dissociation, because what you guys will see is that there's a question in your lab activity called dissociation, and you guys saw that also in equilibrium. The dissociation is not, it's basically the percentage by which the chemical breaks up. So when it breaks up, it dissociates. It basically breaks up to 2 species, the hydronium ion and its anion. So in this particular example, what we have is we have 0.20 molar weak acid. It's 9.4% ionized. So that means that for every 100, 9.4% of it goes on to hydrogen ion and its counter ion. 90.6% of it stays intact. So based on this particular problem, calculate the hydronium, the counter ion, the weak acids, and the Ka for HX. And that's all you really need to know is the percent dissociation to solve this problem. So if you take a look at this, the solutions to this problem, the percent dissociation is basically the amount that dissociates over the initial, how much you started with. So like I said, if it's 9.4, then 9.4 for every 100 will give you that particular reaction. So what you need to do is if you have a 0.20 molar solution, you have to calculate 9.4% of that. And if you take 0.094 and multiplied by 0.2, you get 0.0188. So if we continue with this, here's the ice table. Okay, we have our dissociation right here because we know it's 9.4%. You don't need a Ka for this to solve this problem. All you need to know is how much of it goes to product. Now you can calculate the equilibrium concentrations. And now you've already answered the H plus, the X minus, the HX. And now all you've got to do is take the hydronium ion concentration right here, okay, right here, and basically figure out what the pH will be by calculating the negative log of this concentration right here, 0.0188. And when you do that, you get the pH of this solution. Oops, sorry. And it's hard to control the finer details of this controller. So here it is right here. Okay, we're solving the math. We can calculate the Ka, and you can also calculate the pH of that solution based on that concept. So this particular slide tells you that you can definitely calculate the chemicals based on the percent dissociation. Clear this real quick. So if you want an equation for the percent dissociation, remember that the percent dissociation is X right here divided by the initial right here. And so that's what we have. We solve for X right here, and we divide by the initial right here. And if you do the math, this is the equation you have. Okay, so the percent dissociation, what I'm trying to tell you here is that the percent dissociation of an acid is not constant. The percent dissociation of an acid depends on the Ka. We know that definitely is constant, but it also depends on the initial concentration of the acid. The bigger the acid, right here, the less the percent dissociation. The bigger the acid concentration, the smaller the acid concentration, the bigger the percent dissociation. So that's what that particular math equation tells us. And you can see it in this graph right here. You can see it in this graph right here. This graph tells you that this is the percent ionization in the Y, and this is the concentration of the acid. And notice that as the acid concentration becomes bigger, the percent dissociation becomes smaller, whereas if the acid concentration becomes smaller, the percent dissociation becomes bigger. And this is consistent with Le Chatelier's principle, actually. If you got more particles already in solution, okay, if you got more particles in solution at a higher concentration, then the chemical is not going to dissociate any further because there's already a lot of particles in solution. Whereas if you have very few particles in solution because it doesn't dissociate that much, or the concentration isn't very high, then more of it will dissociate. That's why you see this inverse relationship, okay? So let's talk about polyprotic acids and base, because polyprotic acids and base are one of the things that you will see in your activity, but it makes the acid-base chemistry math a little bit more complicated just because you have to solve multiple equations. But take note that the equations are actually simplified, and I'll try and illustrate to you why that's simplified. First of all, you know it's a chemical that will donate more than one hydrogen because in its formula, it's going to show that there are multiple hydrogens that are ionizable. Ionizable again just means that it's going to break away. So whereas nitrous acid, remember nitrous acid is HNO2, nitric acid is HNO3, whereas nitrous acid is HNO2, that's a weak acid. It only has one hydrogen to donate. That's why it only has one Ka. Sulfurous acid, H2SO3, remember, sulfuric acid is H2SO4. That's a strong acid, but sulfurous acid is a weak acid. And so it's got two Kas for each of the hydrogen that comes off. Now, this second hydrogen over here doesn't peel off until the first hydrogen comes off. So you have to solve the first equilibrium first, use the concentration of the first equilibrium to give you the initial concentration of the second equilibrium. Okay, and then we have a chemical that is triprotic, like phosphoric acid, and it's going to have 3 Kas. So again, these are just examples of polyprotic acids. So what you see here is you're going to see multiple Kas. And here you see hydrogens, multiple hydrogens that are highlighted, indicating that these are the hydrogens that come off. I want you to take note, I guess it's not here. This is phosphoric acid right here. Okay, here, this one right here. And the reason why I want you guys to take note of this is because this is a problem in your activity. It's going to ask you for the phosphorus acid. Phosphorus acid only has two hydrogens that can come off. This hydrogen is not acidic. In other words, it's not ionizable because it doesn't come off the phosphorus cleanly. In fact, the phosphorus holds on to it. That's why you only see 2 Kas. Okay, whereas phosphoric acid down here, this hydrogen's attached to that oxygen, this hydrogen's attached to this oxygen, this hydrogen's attached to this oxygen. It's got 3 ionizable hydrogen. That's why you see 3 Kas. Okay, so I just want you to be aware of that because in your activity, one of the first question is going to ask you for the equilibrium constant for phosphorus acid. And you got to realize that it's only got 2, it doesn't have 3. So don't be searching for a third one. Okay, so let's take a look at carbonic acid and I'll walk you through this so that you can see why, even though you have more work to do when you have polyprotic acid, the work's not that difficult. We have carbonic acid. It can basically give off 2 hydronium ions and become the carbonate. So the sequence is going to be first hydrogen comes off, second hydrogen comes off. But you have to work the first hydrogen, the first equilibrium before you can start on the second. Why do you need to do that? The reason why you need to do that is because you need this concentration right here. You need this concentration right here to start the second equilibrium, okay? Because this chemical right here is not going to be the same as this chemical right here. And so what you do is you set up the ice table for the first one, set up the ice table for the first equilibrium, and you do your basic assumption, and then you can calculate the hydronium ion concentration and the pH of that chemical. And then once you have the hydronium ion concentration, remember that the hydronium ion concentration right here is going to be equal to the bicarbonate concentration, because for every one of these that dissociate, you form equal amounts of this. So this concentration right here is going to be the initial concentration for your bicarbonate, because again, they form in equal amounts. Now that you have your initial concentration of your bicarbonate ion, bicarbonate is HCO3 minus, then you can solve the equilibrium, okay? One thing I want to to show you real quick is a shortcut. I teach analytical chemistry, and we do a lot of acid-base chemistry. So what you have here is the shortcut I want to show you is the following. Whenever you have a, remember that your hydronium ion concentration is basically equal to x squared over, sorry, take that back. The problem that you generally have is you have a Ka is equal to hydronium times the anion times the initial concentration of your acid. Okay, so what you're usually after is the hydronium ion concentration. So if you solve for that, you get this right here. But if we make the assumption that hydronium is equal to A minus, and why do we make that assumption? Because for every hydronium that forms, you get an A minus concentration of equal amount. Then we can simplify this equation and say that what we have here is this term becomes x squared over HA, that's the initial, is equal to Ka. So in other words, whenever you have a weak acid and you can do simplifying assumption, you always want to do this problem. Hydronium ion concentration is equal to, let me just see this, Ka times HA initial, the square root of that. So this is going to be an important equation if you want to calculate the hydronium ion concentration directly. Okay, this is a shortcut. And when you do your activity later on especially the titration, if you use this equation, it'll save you a lot of steps. And here, the reason why you can do that is because you're assuming Ka is small. And if it's a weak acid, Ka is small. So I just want you guys to see that shortcut. Anyway, let me move on. The other thing I want you to know is that in solving this problem, when this thing totally dissociates in water, what happens is that, notice that this Ka right here is 10 to the minus 7, and this Ka is 10 to the minus 11. What that means is that the second hydrogen coming off is very negligible compared to the first hydrogen that comes off. In other words, the hydronium ion from that second equilibrium is negligible. So another shortcut you can do, especially when you see this big change, this big difference in Kas, and this right here is about 4 orders of magnitude, minus 7 to the minus 11. And because it's 4 orders of magnitude, this hydronium is way smaller compared to this hydronium. And so you can make this assumption that the total hydronium in the solution is equal to the hydronium that comes off the first reaction plus the hydronium that comes off the second. But because this is so small, your pH is basically dictated by this first reaction. So again, there are shortcuts involved in acid-base chemistry, and you got to recognize that. And that's what I'm trying to illustrate here, that if the second equilibrium is so small compared to the first, and all they're asking you to do is calculate the pH, don't even bother solving for the second equilibrium, because your answer is going to be the same as the first equilibrium. That is, whatever hydronium ion that you solve in the first equilibrium, that's your answer. And it all goes back to chemistry. If you understand the chemistry, you come to the understanding why that occurs. And the chemistry is based on the Ka. The Ka tells you the efficiency of this reaction. The efficiency is not very good, okay, from the get-go, but here it tells you that's even worse. So you could ignore that. So let me move on and do the next page. Okay, so here's phosphoric acid. This is a good example to go over. Phosphoric acid has three ionizable hydrogen. The first is 10 to the minus 3. The second one's 10 to the minus 8. And the third one is 10 to the minus 13. If the question was simply, give me the pH of this solution, all I need to do is solve this equilibrium right here, and I would be done with. Of course, things are not always easy, okay? Things are not always easy because generally the question is not just give me the pH of the solution. The question is going to be, what are the concentrations of the hydronium and all the counter ions in the solution? And what are the counter ions? H2PO4 minus, H2PO4 minus 2, and PO4 minus 3. The question will be, give me the concentration of all of these. In this case, what you need to do, what you need to realize is that you've got to actually solve all three equations. But there is a saving grace because the equations actually simplify. And let me show you that, okay? Let me show you that real quick. So I want to show you this first reaction. We have the ice table and we have the mass action expression. And again, you can see that if I use this equation right here, let me just show you that. Again, hydronium ion concentration is equal to the square root of the initial concentration of phosphoric acid times Ka. So without doing the ice table, I know that the initial concentration that I'm given is 0.1. So this is 0.10. This is for phosphoric acid. And I know that my Ka is 7.3 times 10 to the minus 3. And so if I multiply this and take the square root of that, go ahead and do the math, okay? What you will see is that the 0.1, 7.3 times 10 to the 3 negative, well, that comes out to 7, well, I shouldn't have done that off the top of my head, 7.3 times 10 to the minus 4, because it's only multiplied by 0.1. And if you take the square root of that, that comes out to 2.7 times 10 to the minus 2, okay? And so isn't this what I got right here? 2.7 times 10 to the minus 2. Again, this shortcut works because you're basically just going straight to the final equation that you need to solve, okay? So this is a good equation to remember, especially if you want to do a quick and dirty hydronium ion concentration calculation. So that's 2.7, but that concentration is also equal to the initial concentration of H2PO4. So look at the second equilibrium. We've got 2.7 times 10 to minus 4, okay? Because that's the acid. That's the acid that we have, because now the second equilibrium is what we call common ion. The hydronium ion that comes off the first has got to be included. Here, let me show you this real quick so that it's clear. I want to make sure that this is clear. So we have our second equilibrium, H2PO4 minus, and that in the presence of water will form H3 plus and HPO4 minus 2. But in the initial line, this guy is 2.7 times 10 to the minus 2. That, yeah, but this also is 2.7 times 10 to the minus 2. And why is that? Because this is the hydronium from the first equilibrium. So it's already going to be in solution. So it's going to be like a Le Chatelier's principle. You've already loaded your solution with hydronium. this equilibrium is not going to be very efficient, because according to Le Chatelier's principle, if you've got more products, it's going to want to shift the reaction to the reactant side. Anyway, now this is 0 because we assume that the reaction hasn't taken place. Now the change will be minus x plus x plus x. And so at equilibrium, what we have here is 2.7 times 10 to the minus 2 minus x. But look at the equilibrium constant for this second equilibrium, 6.2 times 10 to the minus 8. So we can basically assume that this x is going to be very small compared to 2.7 times 10 to the minus 2. So this is 2.7 times 10 to the minus 2, because again, that second equilibrium is small. This will be, the hydronium will be 2.7 times 10 to the minus 2 plus x, and this is just x. So what you have here is the, we can set up the mass action expression. We can say that 6.2 times 10 to the minus 8. Remember, this is Ka2. And why is it Ka2? It's Ka2 because we're looking at the second hydrogen that comes off, is equal to 2.7 times 10 to the minus 2 plus x times x all over 2.7 times 10 to the minus 2. That's this concentration right here. Okay, so look what happens. If we can assume that 2.7 times 10 to the minus 2 right here minus x is 2.7 times 10 to the minus 2, then we should also assume that 2.7 times 10 minus 2 plus x is 2.7 times 10 to the minus 2. So what does that mean? These two will cancel. And what we have is x, which is equal to our HPO4 minus, is just equal to 6.2 times 10 to the minus 8. So remember what I said, even though you have more work in front of you, the math actually simplifies. And these are the things that you got to recognize. You got to recognize that, and what you need to do to recognize this is you got to commit to these assumptions. You got to make that assumptions that this x and this x are negligible. So if these are negligible, this will cancel out, this will cancel out. And what you have is that the hydrogen phosphate is going to be equal to the Ka2. Now, if we work the third equilibrium, we use this concentration as the initial concentration for this guy, HPO4 minus. And then again, what we're going to have for hydronium is it's going to come from the first equilibrium, the second equilibrium. But remember, the second equilibrium was small. So all we have to do here is put 2.7 times 10 minus 2 plus x. Here it's 6.2 times 10 to the minus 8 minus x. Again, we're going to assume that the x is going to be small. Why? Because look at this equilibrium constant. It's 10 to the minus 13. You can assume that the dissociation is negligible. So all we've got to do in this particular case, let me show you that in my iPad, is say that Ka3, which is equal to 4.2 times 10 to the minus 13, is equal to 2.7 times 10 to the minus 2 times the phosphate ion all over 6.2 times 10 to the minus 8. So these are numbers. You can just move these to the other side. And so your phosphate ion concentration is going to be 4.2 times 10 to the minus 13 times 6.2 times 10 to the minus 8 all over 2.7 times 10 to the minus 2. And that's a much easier problem than doing any type of quadratic, okay? So when you have these polyprotic acids and bases, pay attention to the Kas, because the Kas will tell you about the assumptions that you can do, just so that you can see that if you actually worked out the hydronium ion concentrations for the second and third, the second equilibrium gives you a concentration of 6.2 times 10 minus 8. The third concentration gives you 9.64 times 10 to the minus 19. You can definitely see that these are very small compared to the initial concentration of 2.7 times 10 to the minus 2. That's why these simplifying assumptions, especially when you work with weak acids, are going to be your lifesaver. But you have to commit. Okay, you have to commit in terms of doing this. So let me go ahead and move on. I think you have a problem in your activity that deals with polyprotic acids and base. So here's a problem that you guys can do. Sorry, this one, go back real quick. Okay, this one, pay attention to this because the Ka for this is not small. This is sulfuric acid. It's a strong acid. The second hydrogen that comes off is a weaker, but the pKa is 1.9 times 1.99. That means the Ka is 1 times 10 to the minus 2 approximately. So look at that problem and see if you can't calculate the hydronium ion concentration, the hydrogen sulfate concentration, and the sulfate concentration if the initial concentration was 0.5. Okay, see if you can't work that out and submit that, and we'll see about giving you some points. So let me move on. Let's talk about bases real quickly here. Bases are very similar to acids, except now you're looking at the reverse direction. Instead of donating a hydrogen, you're accepting a hydrogen. So the solutions are solved the same way. I want to show you that when you're dealing with base, the hydroxide ion concentration is what you're after. And that is equal, again, to the square root of the Kb times the acid, the base concentration. The concentration of the base, the initial concentration of the base. So I'll just put base initial. Okay, so this is a quick shortcut to figure out the hydroxide ion concentration. And then from the hydroxide ion concentration, you can calculate the pOH by doing this. Whatever this molarity happens to be. And if you're asked to calculate the pH, remember that the 14 at 25 degrees is equal to pH plus the pOH. So the pH is going to be equal to 14 minus the pOH that comes from that. So that basically is the type of problem that you will probably see when you deal with base. They'll give you the base concentration, but they'll still ask you to calculate the pH. So notice that all of these chemicals have lone pair on the nitrogen or some site in their structure where the hydrogen can anchor, because that's the definition of a Lowry-Bronsted base. It's a chemical that accepts a proton. Okay, so and what we have is a Kb right here. Why? Because when it grabs a hydrogen from water, you form hydroxide, as you see right here. All of these are weak bases. And again, from the Kb, you can see which ones are weak base and which ones are strong weak base and which ones are weak base. Okay. Here are more chemicals. Again, I'm just trying to define for you here what are the structural features that makes a base. It's going to have a lone pair, or it's going to have hydroxide to donate. That's the Arrhenius definition. Okay. Again, I want to remind you to do the simplifying assumption. Double check to make sure that you don't have to do more than one iteration. And generally, if your Ka or Kb is in the order of 10 to the minus 3, 10 to the minus 4, definitely you can make these simplifying assumptions. You don't have to go to the quadratic, in other words. okay? And if you do the shortcut, remember that the shortcut that I showed you, you are doing simplifying assumptions. Okay. So, see why this thing is slowing down. Okay. So this is an example of a KB process. And again, if you know how to solve a KA, then you know how to solve a KB. I'll just walk you through this real quickly. What you have is you have a base in the presence of water. The water now donates the hydrogen to the base. You get a conjugate acid. The base becomes a conjugate acid, and then water becomes, which was the acid in the forward direction, becomes hydroxide, which is the base in the reverse direction. We set up the ice table. We know what the Ka is. We basically solve this problem. And again, if you, just so that I can show you that if that was the problem, then the hydroxide ion concentration is just equal to the square root of the Kb times the concentration of the initial concentration of C2H5NH2. So we know that Kb is 6.4 times 10 to the minus 4. We know that the initial concentration is 0.075. Take the square root of that, we get the hydroxide. And if you do the math, you get 6.93 times 10 to the minus 3. That's your hydroxide. And if you take the negative log of that, that's 2.16. And if you subtract 14 from that, you get 11.84. Remember, the higher the pH, the less acidic it is, the more basic it is. So this pH of 11.484 is consistent of a basic solution. This right here in highlighted is basically this equation that I just did, this equation right here, okay? It's Ka times the initial concentration of the base. This could be the initial concentration of any base, and take the square root of that. So I want to show you this because this is an important concept to know. Suppose you're given F minus, and you say that I have an initial concentration of F minus of 0.010, but you don't know the Kb. You don't know that. Well, you can look up the HF, and the HF has a Ka. I think I showed you back there, what had somewhere in the order of 10 to the minus 4. Okay, I want to show you that the Ka and the Kb is equal to Kw. Okay, and that's what this derivation is. This derivation right here, in fact, your Ka, according to this slide, is 3.5 times 10 to the minus 4. So let me just do this for you. If my Ka is equal to 3.5 times 10 to the minus 4, and I don't know what my Kb is, then I can just do this. 1 times 10 to the minus 14 divided by 3.5 times 10 to the minus 4. That's from this equation right here, equals Kb. Okay, so if I do that math real quick, you got to have a Kw though. And remember, Kw is not necessarily 1 times 10 to the minus 14, depending on the temperature. If I do this math, this comes out to 2.86 times 10 to the minus 11. That's my Kb. Notice that 10 to the minus 11 and 10 to the minus 4 are sort of in opposite of the spectrum of 0 to 14. That's why I said that if you have a fairly strong weak acid, then the base is going to be a very, very weak base. And that's because of this relationship right here. Anyway, this equation just shows you in a mathematical relationship and through the chemistry that Ka times Kb is equal to hydronium times hydroxide. Don't assume, however, that Ka equals hydronium, okay? It just tells you that that relationship holds. Ka times Kb equals Kw. So all you need is either the Ka or Kb to calculate the other, as long as you know Kw. Okay, so here are examples of an amphoteric substance. What is an amphoteric substance? Amphoteric substances are chemicals that are going to dissociate, or amphoteric means it's got dual properties. It can be a proton donor or proton acceptor. It can go either way. And so if you take a look at carbonic acid, H2CO3, it forms bicarbonate, HCO3, and bicarbonate can go further to carbonate ions, okay? But if you look at carbonate in the process of the base and to produce hydroxide, if you put it in water, it forms bicarbonate, and that can go further to form carbonic acid. If you take a look at these two right here, okay, these two right here, and the reason why I color code them, 4.3 times 10 to the minus 7 times 2.33 times 10 to the minus 8 actually comes out to 1 times 10 to the minus 14. And these two right here is also such. And the reason why that's the case is because of this this concept right here. Let me try and illustrate that. When you have carbonic acid, H2CO3, and it forms bicarbonate, HCO3, and it forms bicarbonate because it releases the hydrogen, okay? And then this releases the hydrogen to form carbonate ions. Then the reverse process is the carbonate ions picking up a hydrogen and the bicarbonate ion picking up another hydrogen, okay, to form that. So in one direction, this direction, it loses hydrogen. In the other direction, it picks up hydrogen. So this is the acid process in which it donates a hydrogen. This is the base process in which it accepts a hydrogen. These two right here are conjugate pairs. These two are conjugate pairs. Why? Because they differ by a hydrogen. These two right here are conjugate pairs. Why? Because they differ by a hydrogen. So the only time the Ka and Kb equals Kw is for conjugate pairs. So the Ka, let me change pen here. The Ka1, this is Ka1 because it gives out the first hydrogen. This is Ka2 because it gives out the second hydrogen. On the other hand, this is Kb1 because it picks up the first hydrogen, and this is Kb2 because it picks up the hydrogen. So Ka1 times Kb2, why? Because these are the conjugate pairs, equals Kw. And here we have Ka2 times Kb1 equals Kw. Oops. Just real quick. Kw. So it's only the conjugate pairs that forms this relationship between Ka and Kb. You can't, in other words, you can't use the Ka1 here and relate it to the Kb1 here, because according to this, the Kb1 and the Ka1 are not conjugate pairs of each other. Okay, they're not conjugate pairs. That's why you can't do that relationship. They have to be conjugate pairs. So that's one thing that I want you guys to see. So this is a problem. You guys should take a look at it. Let me clear this because we're running out of time. Okay, this is the example. So HCO3, if you put a sodium in front of HCO3, so we have NaHCO3, we have baking powder. Okay, or sorry, not baking powder, baking soda. Sodium bicarbonate, NaHCO3, sodium bicarbonate. And you can introduce HCO3 by simply putting sodium bicarbonate, baking powder, because the sodium is going to be a spectator and you have bicarbonate. And the question is, if you have bicarbonate, in which direction? Is it a stronger acid? Sorry, is bicarbonate going to follow this path, or is it going to follow this path? Okay, so answer that question. Which path do you think bicarbonate will go? Will it go towards carbonate ions, or do you think it'll form carbonic acid? And the key to this question is look at the equilibrium constant. Okay, so let me move on, and then I'll finish this discussion. So let me go ahead and finish this because we're practically towards the end here. Here are other amphoteric substance. Okay, and so that's the question that I have right here is if I have baking soda, is the baking soda, if I put it in water, is that solution going to be acidic or basic? So you guys can take a look at that. I want to start where we left off last time. And where we left off last time, well, let me just show you what happened last time. Okay, discard. So this is still 16.02, and in 16.02, we're covering, we talked about baking soda, and I put on the discussion board what would the pH of baking soda would be if you had 42 grams of baking soda, sodium bicarbonate, and you put in 500 milliliters of water. So take a look at that. It's a couple of points if you can get through that. And then we covered solubility of salts. Here, let me try and give you the background. If you put a salt, and it's not an ordinary salt, it's a salt that have acid-base properties. And you know it has acid-base properties, and we're going to be actually discussing this in more details in the next discussion. For example, we have barium fluoride. Barium fluoride dissociates to barium ions and fluoride ions. But you guys should recognize that the fluoride ions, sorry, take that back. It's not -2, it's 2 fluoride ions, okay? You guys should recognize that the fluoride ions is the conjugate of HF. Because it's a conjugate of a weak acid, that means it has acid-base property. Okay, so whenever you see a salt, first make sure you know how it dissociates to its cation and anion, and then investigate the ions further to see if it's the conjugate of a weak acid or a weak base. If it's a conjugate of a weak acid or a weak base, then it's going to have acid-base properties. Okay, so that's basically what happens. So this is the reaction that I just showed you. What will happen is that in water, the fluoride ion is going to react with water, and because you guys know it's the conjugate of a weak acid, HF, then F minus is a base, and what it'll do is it will extract a hydrogen from water to produce HF and OH minus. Even though HF is an acid, OH minus makes the solution basic. So what happens is that when you put barium fluoride in water, the solution have a higher pH than 7. The solution is basically basic, okay, because of this reaction right here. Now, suppose because barium fluoride has a solubility limit, okay, you can find the solubility limit by looking up the KSP, but you can actually force this chemical to dissolve further, that is, force the equilibrium in this direction, if you put a chemical that will consume the fluoride ions. And if you put in a chemical in water that will consume the fluoride ions, then it'll force the equilibrium to the right. So what are the chemicals that would consume the fluoride ions? Any chemical that will consume hydroxide. So if you put an acid in solution, what will happen is that any hydroxide that forms from this equilibrium is automatically reacted with hydrogen ions to produce water. And because you're removing hydroxide from this equilibrium right here, then the fluoride is going to be moving to the right, which makes the top reaction, okay, move to the right as well. So that's how you determine whether or not a salt could be altered in terms of its solubility by looking at the chemicals that it produces in water and see whether you can add a chemical that will cause it to be consumed further. Okay, so let me go ahead and clear this real quick, and then oops, and then I'll show you that. So fluoride reacts further, decreasing the amount of F minus by equation 1. As HF is produced, more, see how HF is produced here, more barium fluoride dissolves to maintain the KSP, to maintain the equilibrium constant. F minus cannot be removed further by addition, can be removed further by addition of an acid. And therefore, you can cause the solubility of this particular salt by introducing acid. On the other hand, if you don't want to increase the solubility, you want to decrease the solubility, that is, you don't want it to dissolve further. Instead of adding acid, what you want to do is add base. Because what base will do is that it'll load up the hydroxide. It'll cause the equilibrium to shift to the left, causing this to go up, and it'll cause the equilibrium to shift by adding more hydroxide, which causes the equilibrium to shift to the left. Then the fluoride in the first reaction increases. It causes the equilibrium to shift to the left and therefore decrease the solubility. So depending on the salt, if it's got acid-base properties, and you can tell if it has acid-base properties because you can investigate the ions. If the ions are conjugates of acids and bases, weak acids and weak base, then it's going to have acid-base influence in terms of their solubility. Okay, so uh, so factors affecting solubility, basic solution. Again, what we can have here, this is basically what I just told you. What you want to do is you want to add hydroxide. It causes it causes an increase on that hydroxide right there. It shifts the solubility, it shifts that equilibrium to the left. It causes the first reaction to cause the equilibrium to shift to the left, and therefore the solubility decrease. Okay. So the other thing that I want to cover, this is probably the last part, is if you have a whole bunch of um, salts or ions in solution, how could you determine which is the strongest of the chemical in terms of acid properties and which is the weakest? So what I'm going to do is I'm going to show you this reaction. If I give you this reaction between hydrogen, if you put hydrogen sulfide in water and I ask you, which way does the equilibrium lies? Does it favor the product? That is, if you have a beaker, okay, and you put H2S and water in water, which is the dominant solution? H2S, water, H3O plus, or HS, the conjugate of H2S? And how you want to answer that question is you got to take a look at and see that this reaction really is a competition between two acids. This is your first acid, this is your other acid. Between these two acids, which is the stronger acid, H2S or H3O plus? Well, H3O plus is one of the strongest acid out there. We haven't mentioned it because we've sort of mentioned it only through the fact that it forms, but it's one of the strongest acid out there. Plus, you also know H2S is a weak acid because it's not one of our top seven. So to answer that question, the dominant chemical in this mixture right here would be hydronium and HS because sorry, the dominant chemical, I take that back. Let me erase that. The dominant chemical, because this thing is going to be shifting to the left and very little to the right, because this is a weak acid, this is a stronger acid. So the stronger acid is going to dominate that tug of war. So because the equilibrium is shifting to the left, the chemicals that are going to be the largest in quantity is H2S and H2O. Okay, the least amount will be H3O plus and HS. So that's how you determine between two acid which is the stronger acid by looking at the competition to donate hydrogen. Okay, so let's take a look at other examples. And here's another one. We've got H2PO4 and actually that's the wrong chemical. That's the wrong acid. The acid between these two is that. The acid between these two is that. So you're looking at the competition between this acid and that acid. And so what if you look up the Ka value, you'll see that the phosphoric acid is actually a stronger acid with a bigger Ka than ammonium. So since phosphoric acid is the more dominating acid, the equilibrium is going to shift to the left. So the dominant chemical in solution are going to be H2PO4 and NH4 plus. Okay. So again, it's the tug of war between two acids that are in opposite side of the equation. The other examples are um, hy- per, perbromic acid. This is a perbromic acid and bromide acid. So which between these two is the stronger acid? This is a stronger acid because it's got more um, oxygen, and you see that in the next discussion. If this is a stronger acid, then that's going to dictate that it gives up its hydrogen. The equilibrium is going to shift to the right, and these are the chemicals that are going to be the largest amount in quantity in the mixture. And then finally, in this last example right here, okay, we have acetic acid and hydrogen cyanide. Now, what you need to do, because I don't know off the top of my head, I believe acetic acid is the stronger acid, but in order to figure that out, you probably need to look up the Kas. The bigger Ka is going to be the one that is the stronger acid, and then you can determine whether or not which chemical is going to be the chemical that dominates the solution. So if we have all of these in a beaker and we want to figure out the relative strength of these acid, you can see that hydronium is the highest. Um, H2S is somewhere in the middle. Ammonium is somewhere there. Phosphoric acid is actually higher than those. Dihydrogen phosphate, um, bromic acid, and if you don't know how this arrangement works, you can just look up the HKA for each one of these. Okay, so these are the chemicals I believe that was in that discussion. So anyway, just make sure that if you're looking at a reaction and you're trying to determine which way the equilibrium favors, the stronger acid is always going to dictate the show. Okay. So there's a question here. So does it have to do with the bond strength of the hydrogen? Yes, it does. And that's what we're going to be covering. Okay. Remember that the acid is defined as the um, willingness to give up its hydrogen. So the weaker the hydrogen, the bond is to the hydrogen, the more willing it's going to donate that hydrogen, which makes it a stronger acid. So if it has a very weak hydrogen bond to another element, then that makes it a stronger acid. Okay, so yeah, that's a good question. Do we need to memorize acid strength order? You guys will have a Ka value. Okay, and then in the next discussion, even if you don't memorize the Ka values, you could actually figure it out which is the stronger acid based on some um, chemical structure properties. And that's what we're going to be talking about shortly. Okay. And that's going to be important because if you do take the MCAT, they probably won't give you any Kas. You're just going to have to figure out which chemical is a stronger acid because of its structural properties. And the next discussion will make that clear. Okay. So let me go ahead and clear that. And I think that's the rest of the structure. This is a table that you can find in your book. If you can memorize it, great. If you have a list, great. But if you don't have a list and you only have a structure, then the next discussion, um, lecture 16.03, will show you how to make that deduction. Okay. Here's a bunch of questions that you guys can take a look at. And it's basically a lot. All these questions is about calculating pH. Okay. And in fact, that's what acid-base chemistry is about. We want to know how acidic that solution is. So take a look at that, see what you have. If you look real closely, the answers are over here. So if you have the PowerPoint slide, just blow it up 20 times and you'll see the answers. Okay. So let me go ahead and wrap this up.